This is part 2 of section 7.5. This section is on work, springs, pumping, lifting type problems. So this specific part is going to focus on pumping problems. To find the work needed to pump all or part of a liquid from a container, we're going to turn to integration. That's because when we're talking about pumping problems, the liquid has variable depth. So variable depth means, when we try to use that work is equal to force times distance, that distance is variable. So we're going to need to use an integral. We're going to do this by removing one thin slab at a time of whatever this liquid is. And what we're going to do is use the volume of each slab times the weight density of whatever fluid is there to get the full weight of each slab. That's going to be, of course, our force. And then the distance is going to be, however far it's needing to move in this pumping process. So the formula that I gave you, the really informal formula that I gave you on the formula sheet, is this. I wrote more on this one than I did on the formula sheet. Just a little bit more explanation here. We have the area of the slab, the weight density of the fluid. I usually just put weight on here. But technically it is the weight density of the fluid. The weight density and weight are different. The weight is the full weight of how much water you have or whatever liquid it is. The weight density is going to be a weight per unit volume. So we're going to have to multiply it by the volume. And that's probably easier to see as we go through examples. And then the distance moved. This little du out here, we're going to typically orient this to where we are pumping up or down. We're going to be moving in a y direction. So this is more often than not going to be a function of y. My area of the slab times this little du out here is going to together make up my volume. And then when I throw the weight density in there, these three together make up the total weight of the slab. Because this is, how much volume the slab holds, and here's the weight per unit volume. So that's going to be my force, and then of course that's my distance. Remember, the English unit of work was foot-pounds, and the metric unit was Newton-meters. So let's just dive into our first example. So how much work does it take to pump the water from a full upright circular cylindrical tank of radius 5 meters and a height of 10 meters to a level that is 4 meters above the top of the tank? The weight density of water is 9,800 newtons per cubic meter. So of course that's this a little bit more straight. This weight density is this weight per cubic meter. So that's per unit volume here. So it means that's how much this particular amount of water weighs. So 1 cubic meter weighs 9,800 newtons. Okay, so circular cylindrical tank, a cylinder with a circular upper and lower base. So it's going to look something like this. We know that the base, both of them, are circular and has a radius of 5. So that's where this and this come in. So that's how we know that's 5 and that's negative 5. I did it to where that circle was centered, kind of sitting right there on that x-axis. It has a height of 10. Now, I don't know if you can get this from my drawing because I'm not the best artist, but I'm trying to draw that in the middle here to where it looks like you're looking at the top, like you're looking down on it, and this top right here is sitting at 10. It looks like it's right in the middle of that circle, but I'm trying to give the illusion that this is three-dimensional and that top right there is at 10. I don't know if it's giving that vibe to you or not, but that's what I'm going for. So, and it says you're pumping it to a level that's 4 meters above the top. So if the top is at 10, 4 meters above would put you up here at 14. When we start looking at these slabs, we start taking these cross sections in here, okay? We're going to get these little circles in here, and each circle has a little infinite thickness, and that's my dy. That's not an I, that's just a little indication there that little thickness right there is my dy. Because it's a circle and it's the same throughout, like a circle down here has the same radius as a circle up here, then we know that the area of the circle is pi r squared, the radius being 5 throughout here, means that the area is going to be pi times 5 squared. So let's talk about how to set up this integral. Okay. We have the area of the slab. This first one is fairly easy because these slabs are all the same. The circle all throughout this tank are all the same. So here's the area of my slab, pi r squared. Here's the weight of water that was given in the problem. The liquid is located from 0 to 10. So again, I'm trying to give the illusion that this is sitting on that origin. So this isn't technically dipping down here into that negative. I'm trying to give the illusion that it's sitting on 0. So the liquid's located from 0 to 10 because it said the tank was full. Alright, so this is where some confusion might come in. Where did I get 14 minus y from? Well, the distance each slab has to move. So we're pumping it to this level 4 meters above the top of the tank. Let's say that this slab right here is at, I don't know, let's say that it's at 5 meters. If this particular one's at 5 meters, how far does it have to move to get up here? Well, it's got to move 9, right? Because it's 14 minus 5. It's got to move 9 meters. If you have a slab down here at, say, 1 meter, it has to move 13 meters, that 14 minus 1. So think of this as upper minus lower. Okay? That's my distance that it has to move. So upper minus lower, and my lower is a variable because these slabs are going to vary because I'm having to pump out all of this stuff. So then it's just a matter of putting all this in the calculator and boom. Because this was all given to me in terms of meters, newtons per cubic meters, that tells me that my units are going to be Newton meters. That's going to be metric units. These get messier if this is not a straight line. If we have something that's, say, cone-shaped, to where these circles aren't the same throughout, if they're varying in size, then, of course, this is going to have a variable to it. But I started off with a cylinder because, you know, it's a little bit nicer. We can see that radius of all these circular slabs is going to be 5 throughout. All right, speaking of conical shaped stuff, let's look at a conical shaped tank. So it's a tank that's shaped like a cone. Oops. It's filled to within 2 feet of the top with olive oil that weighs 57 pounds per cubic foot. So that's what we call the weight density of olive oil. So that's how much a cubic foot, that volume of olive oil, that particular volume, 1 cubic foot, weighs 57 pounds. How much work's done in pumping all of the oil to the rim of the tank? We typically talk about pumping problems as going to like some specific point. Sometimes that point is just the rim of the tank because gravity can take over. It could just be that you need to pump it out of the tank, and then there's like some kind of a tube. Once you get to the top of the tank, gravity takes over and you don't have to worry about the work involved in pumping it any further. So the cone, this conical tank, looks like this, to where the circular base is upright and it's kind of sitting on this tip down here. It has, this circular base has a radius of 5 units. And the conical tank itself has a total height of 10 feet. So again, I'm putting that 10 in the middle, trying to give that illusion that you're kind of looking down on the tank, and this is the that circular base. I know it's weird to call that a base when it's not sitting on it, because we think of base as being the bottom, but it is technically the circular base of the cone. This cone is just oriented to where the base is up. Okay, so it's got that height of 10. It's filled to within 2 feet of the top. So that's where this 8 comes in. So there's where it's filled. I have these points at 5'10" and -5'10". So I gave you those because the radius of that circle there was 5. Now, if we look at these little slabs, you can see that a little slab down here has a little teeny tiny radius, and the slab up here has a slightly bigger radius. The radius varies throughout the cone for these slabs. In order to find that radius, we're going to need to find the equation of this highlighted line. So that line from 0, 0 to 5'10". So just highlighting that because that's the line I'm looking for. So we have that this goes from the origin right there, 0, 0, to 5'10". That's a pretty nice line, right? As far as like slope and having to find the equation of that line. If you just look at rise over run, we get 10 over 5. Okay, so a slope of 2. The y-intercept down here at 0. Or 0, 0. So we get a b value of 0. Okay, so we just get a nice little y equals 2x. Because we're talking about pumping it upward in a y direction, everything needs to be a function of y. So I took this equation of this line, y equals 2x, and rewrote it as x as a function of y. Alright, so now we're ready to set up our integral. I'm going to integrate from 0 to 8. So why am I only integrating from 0 to 8? If this tank is 10 feet tall, why didn't I integrate from 0 to 10? The cylinder was also 10 feet tall, and I did integrate from 0 to 10. So why am I only doing to 8 this time? Well, that's because this tank right here was full. So the liquid was located from 0 to 10. Here, my liquid is located from 0 to 8. Right? So here my liquid is located from 0 to 8. My slabs are circles, like they were in the last example, so I'm still going to need pi r squared. My r is following this line, which we found to be this equation, this y over 2. So we have pi r squared. And then we've got the weight density of the olive oil, Then we have this, the distance that it has to travel. Once again, this is upper minus lower. Upper being 10, that's the rim, that's the top of the tank, because it says how much work is done in pumping all the oil to the rim, so that upper rim of the tank. So we're pumping it to that level of 10. So how far does this little slab have to go? If this little slab right here is at, say, 3 feet, well, it's got to go from 3 to 10. So it's got to go 7 feet, right? Because you can have 10 minus 3. So it's that 10 minus the Y value of your slab. Whatever the Y value associated with your slab, 10 minus that Y value is how far that slab has to move. So you're going to see this pretty often, that we're going to have this area, weight, and then this distance. That distance, you're going to notice, is going to be some subtraction involving the variable of integration. Okay, let's look at another shape, because that's really what I'm doing here. Is I'm just doing a bunch of these pumping problems of various crazy shapes. So we started with a nice little cylinder, and then we were like, okay, let's just kind of tuck it in a little bit and give it a cone. Now it's like, okay, let's look at a hemispherical tank, a hemisphere being half of a sphere. So a hemispherical tank of radius 6 feet is positioned so that its base is circular. That means that if you're looking at this hemisphere, so you can see I drew a full sphere here, but I positioned it to where that upper part of that sphere is sitting on that x-axis. So that's what it means by the base being circular. That if you cut a sphere in half, that cross section is going to be a circle. How much work is required to fill the tank with water weighing 62.4 pounds per cubic foot through a hole in the base if the water source is at the base? So we are pumping the water in. The last two examples, I was pumping the water out. Now I'm pumping the water in through the base. All right. The hemisphere, if I start taking cross sections, they are circles. Okay. It's not always circles. I'll get to another one that's a weirder shape. But this one is going to have a cross section of a circle. The radius is going to vary along that hemisphere. So we're going to need to find the equation of this highlighted curve. Well, that's just the equation of a circle. Okay, so the highlighted curve is just a circle, radius 6, center 0, 0. So we know the equation of a circle is x squared plus y squared is r squared. Now let's find the equation of the right half of this circle, because that's the curve that this r is following. The right half, of course, is going to be the function of y, because it's going to be, the upper half is y as a function of x, positive one and then the negative one. This one, if you do x as a function of y, the positive of the plus and minus, the positive is going to be the right half, the negative is going to be the left half. So let's take this equation, this x squared plus y squared is 6 squared, and let's solve it for x as a function of y. So first subtract over the y squared, and then take the plus or minus square root. The plus is the right half, the minus is the left half. This radius is following that curve. So my work done is going to be the integral from 0 to 6. Okay, why is it from 0 to 6? Well, because I'm filling up the tank. So I'm looking to fill this tank. So from 0 to 6. Remember down here, this stuff down here, I only put this stuff in just to show you that it was a circle. So none of this is part of my hemispherical tank. Only this upper part up here is my hemisphere. This I just put in just to show you that that's the equation of a circle. So that part right there is my hemisphere. So my slabs are going to run from 0 to 6. That's where the liquid's going to be. Pi r squared. Remember, r is following this curve. There's my weight density of water. And this is new. My y value. That's, of course, the distance that the slab has to travel. This is a little weird here. Where did this y come from? Well, you know how I've said in that the last two examples that you do that kind of upper minus lower? Because we're pumping in through the base. Remember, we're pumping water in through a hole in the base. The water is moving from 0 upward. So if this slab right here is, say, at 5 feet, how far did it have to travel? Well, it went from 0 to 5. So this is upper minus lower. If you want to think of it that way, it's just y minus 0. Y being the upper, my lower being 0 because I'm pumping in through 0. So this subtraction's backwards from what we were doing with the other examples. That's because the other ones were pumping upward and out. This is pumping upward but in. So wherever that slab ends up, that's how far it had to go. All right. Now, when you put this in your calculator, look, that's going to be really ugly. All right. Just notice that you have a square root squared here. So maybe just don't type in the square root or the squared. You know those two are going to undo each other. So when you go to type this in your calculator, just use pi 36 minus y squared times 62.4 times y. Okay, one more, and this one's not going to have circular cross sections. So let's find the work done in pumping water over the rim of a tank that is 50 feet long, has a semicircular end of radius 10 feet, and I'm giving you a picture to go along with that. If the tank is filled to a depth of 7 feet with water weighing 62.4 pounds per cubic foot. All right, so I did my best artist representation here of what this looks like. All right, so this is a tank. It is a rectangle on the top, and we've got these semicircular ends going on. So what this tank looks like, it looks like if you had a cylinder laying, on a side, and you just sliced off the top half of it. Our slabs that are being pumped are rectangles. Now I do want to get a close-up of this semicircular end here, so that's where what I did over here. So I was like, all right, let's look at this semicircular end. So I did a full circle over here, but I oriented it to where my center was at 0, 0. In doing that, it made things a little weird, right? So I oriented it to where this point right here, this part right here, is going along that x-axis, so that the center of my circle, right there, that point right there, was going to be at 0, 0. That's because the equation of a circle is so much nicer if the center is at 0, 0. You don't want to have to mess with the x minus h quantity squared plus y minus k quantity squared equals r squared business. So here's what the full circle would look like. Of course, we're only dealing with the semicircle on the bottom. I only did the full circle to show you there's that equation. Once again, I solved it for x. We have the right half and we have the left half. So we got the right half of the circle, we got the left half of the circle. Now, where did I get this -3 business? Well, it says that it's filled to within a depth of 7 feet of water. So a 7-foot depth, if this is at -10, this is not drawn to scale, by the way. If this is at -10 and that's a depth of 7 feet, that would put that right there at -3. All right. These slabs, let's go back to talking about them. They're rectangles with a constant length of 50. The width is going to change. So a little rectangle slab down here is going to have a more narrow width. It's still going to have that length of 50. The width is going to be controlled by the semicircle. All right, so the width of this rectangle is controlled by the semicircle, and it's the distance from one side to the other of the semicircle. So we know way back from section 7.1 how to find the distance between two curves, that it's just right minus left. So we have the right and the left curves. We have those equations over here for the right half of the circle and the left half of the circle. So this total distance is right minus left. So if I take the positive up here minus the left, which is the negative, you know, that's just going to be a plus. Those are like terms, so you just get 2 times the square root of 100 minus y squared. This is not a pi r squared situation because these are not circles. Right? They're rectangles. In fact, they're rectangles, and I should have got my color coding. I should have kept that going. There's the area. So I've been doing it each time where my area has been in red. So this is the area of that rectangle. So there's my area, my rectangular slab, my weight density of water, and then I've got the distance that it has to travel. All right, those distances, man, they're not always the same. And I'm trying to do examples of a bunch of different ones so that you'll have an example of one of everything, so that when you run into it, you'll kind of know what to do. All right, so here, we're pumping the water over the rim of the tank that's 50 feet long, blah, blah, blah. So we're pumping it to that 0 level right there. All right. Oh, and I forgot about the bounds there, that I'm going from -10 to -3. That's where the water's located, from -10 to -3. It looks weird to have it there like that, but I swear I oriented this like this on purpose to where that center was at 0, 0. It made this and this equation nicer, which made this nicer. Trust me, these numbers being ugly are a small price to pay to have this and these equations be nicer. All right, so the liquid's located from -10 to -3. We've got the area of the slab, length times width, weight density of water, and now the distance the slab has to travel. So if it's traveling up to the rim is 0, right? 0. And then the y value down here, so it's going to be upper minus lower. So that's 0 minus y. Now check it out. If you have a slab down here, let's say that you've got a slab at, say, like -6. How far does it have to travel? Well, it's got to travel 6 feet. So if it's at -6, that minus -6 means it traveled 6 feet. So you can see how that kind of works out there. But that does come from the, the level that you're pumping it to minus that y value, that upper minus lower business. And then, I'm going to leave this one for you to put in your calculator, because we've done a ton of these at this point. If you guys get something different for any of these answers than what I got, please let me know. And if you're having any problems, kind of understanding these or following anything that I did, please let me know. Send me an email and, let me know where you're stuck, where you're, struggling and stuff. So, all right. So that concludes part 2 of section 7.5.